So in this video, we're going to talk about a different kind of bonding called covalent bonding, where instead of transferring electrons from one atom to another, atoms decide that they will share electrons in order to achieve the full outer shell required by the octet rule. So I've gone ahead and written down covalent bonds here, and I drew two fluorine atoms just with their Lewis dot structures. In our last video, we talked about fluorine, and we drew fluorine out with all of its protons and neutrons and electrons. So you understand what's in a fluorine atom. I know you do. So we're just going to shortcut and just put an F instead of the nucleus and just put the Lewis dots instead of drawing all of the atoms or all of the electrons. So in the valence shell of a fluorine atom, there are 7 electrons. 1, 2, 3, 4, 5, 6, 7. How many does it want? It would really like to have 8. Now, the way it can do that, if it doesn't have anything that's available to give it some electrons, is that it can just borrow some from another fluorine atom. So if this fluorine atom sees another fluorine atom, and yeah, we're personifying this a little bit, but it can say, hey, can I borrow one of those electrons sometimes? And this fluorine atom says, well, sure, but I want to borrow one of yours sometimes too. And this fluorine atom says, yeah, that seems fair. Okay. So if they bond together, if they stick together really closely, they can each use one of each other's valence electrons if they need to. That's called a covalent bond. It's very, very simple. It's just a sharing bond. This is called a single covalent bond because they're sharing one pair of electrons. So there's also a double covalent bond that happens with things in the oxygen group. Because the oxygen group, you remember, has 6 valence electrons. So let's draw sulfur. Here's sulfur nucleus, and here's 1, 2, 3, 4, 5, 6 valence electrons. Let's draw ourselves another one too. So here's another sulfur atom with 6 valence electrons. Hopefully you can see how this would work. This one would say, hey, can I borrow 2 of those sometimes? And this one would say, sure, yeah, but let me borrow 2 of yours sometimes too. They're both stable. They both have access to 1, 2, 3, 4, 5, 6, 7, 8 valence electrons by sharing them. This is a double covalent bond because they have 2 pairs of electrons shared. Excuse me. What about a triple covalent bond? Does that ever happen? Yes, it does. Nitrogen is the most abundant element in the Earth's atmosphere. There's lots of nitrogen all around us. Nitrogen, and I'm drawing these Lewis structures in a sort of dumb way just because the circles are easier to draw. If I put 3 electrons on one side of my nitrogen atom. So here's my nitrogen atom. It has 5 valence electrons. Let's look at it here. See, it's in this group, the 5 valence electrons. So this nitrogen can say, hey, can I borrow 3 of those sometimes? Yeah, sure, but only if I can borrow 3 of yours sometimes. Okay, that seems fair. A triple covalent bond. Now, if you had to guess which one of these is the strongest, hopefully you could see that the triple covalent bond would be the strongest because it's just held, these 2 atoms are held together more tightly because of that triple bond. Let's see. There's a special kind of covalent bond called a hydrogen bond that I would like to draw you a picture of as an example of a molecule that has multiple bonds in it. So oxygen is in the same group as sulfur. It has 6 valence electrons. 1, 2, 3, 4, 5, 6. Well, there is, let me tell you, a whole lot of hydrogen in the atmosphere. So when there's oxygen looking for some more valence electrons, it's pretty likely to find a hydrogen. The hydrogen, remember, needs 2 valence electrons to make its full outer shell because it's so tiny. It can say, hey, oxygen, can I borrow one of those? Oxygen says, sure, yeah, let me borrow one of yours sometimes too. Now, hydrogen is stable, but oxygen still isn't. See how hydrogen has a full outer shell? Oxygen still needs 1 more. But where there's 1 hydrogen, there's going to be another one. So oxygen can find itself another hydrogen. This is a special kind of bond called a hydrogen bond, but it's a single covalent bond, right? So if on the test I showed you this and I said, what kind of bond is this? And I gave you some options. If I said, well, is it a double covalent bond, or is it a triple covalent bond, or is it two separate single covalent bonds? Hopefully you'd be able to see that this is a single covalent bond. See how it looks like this? They're sharing one pair of electrons. And this is a single covalent bond. We've made water. H2O is water. And it's composed of 3 different atoms composing one molecule, and there are 2 separate single covalent bonds here. While we're talking about covalent bonds, I want to use the rest of this paper to do a few other little odds and ends of things that you need to know for the test. Let's see, the definition of the word molecule, M-O-L-E-C-U-L-E, is an arrangement of atoms held together by bonds. So this is a fluorine atom. It's only composed of 2 fluorines, but it's a fluorine atom. We'd call it F2. This is a sulfur atom, or a sulfur molecule, sorry. It's composed of 2 sulfur atoms. We'd call it S2. We'd call this N2. We'd call this H2O. Each of these is a molecule. It's an arrangement of atoms that are held together by bonds.